if I have two vectors, like a vector like maybe this, that's 10 meters, and then a vector like this that's maybe 5 meters, and I asked you to add those vectors together, how would you do that? 10 plus 5 is 15. 10 to the east, 5 to the east gives me 15 to the east, right? That's easy vector addition. That's almost like grade 1 math, isn't it? Right, where you have to add two vectors together, but they're both in the same direction. Well, what if we had something like this? What if we had 4 meters this way, and we had 3 meters this way? How do we add those ones together? What is it? Yeah, we say 4 plus negative 3. This is more like, I don't know, like grade 5 or grade 6 math, where you have to add negatives in there, right? We're still adding vectors, but the vector addition here is harder than it was with our grade 1 math, 10 plus 5, right? 10 plus 5 is equal to 15. Okay, 4 plus 3 could be either be equal to 7 if they're in the same direction, or they could be negative 1 or positive 1 if they're in opposite directions. Good? I haven't really taught you anything new here yet, right? This vector addition you can already do. But what if we've got this? What if we've got 4 meters this way and 3 meters this way? How do we add those vectors together? What's the sum of those vectors? Well, there's a direction because we're adding vectors together, so you do need to include a direction, but we need to include a magnitude as well. I picked those numbers because this is a doable one in your head, actually. Some of you might know. 3 plus 4 in this case is equal to 5. 3 plus 4 is equal to 5. We're adding vectors together that aren't on the same plane. We're adding vectors together that are on the x-axis and other vectors that are on the y-axis. And the goal, every time we're adding vectors together that are on different planes, x-axis, y-axis, the goal is to get a right-angled triangle. That's what we've got here, right? We've got a right-angled triangle. Once we have a right-angled triangle, we can do the Pythagorean theorem. Do you guys remember that? A squared plus b squared equals c squared, right? To solve for the hypotenuse. And then we can use the inverse tan function to find an angle, which is our direction there, right? We're not east or west or north or south here. We're at a certain angle from the east in this case. Does that make sense? Now, some questions are going to be harder than just, here's a 4, here's a 3, do the Pythagorean theorem, do the inverse tan function. But that's the goal. We always want to get to that spot. We always want to get to the spot where we have a simple right-angled triangle, which allows us to do two things: Pythagorean theorem and the tan function to find theta. Got it? So what's the goal? What's the goal? To get a right-angled triangle. Okay, right-angled triangle. We call it a right-angled triangle vector diagram. And I'll explain exactly the rules on a vector diagram here as we go through. Okay, make sense? This, easy. This, pretty easy. A little harder, but still pretty easy, right? This isn't so bad. Okay, this isn't so bad once you recognize how to do it. Okay, so remember, I mentioned a second ago that this is our x-axis, this is our y-axis. Remember that, because, listen, if you're given two vectors that you want to add together, 3 and 4, and one's on the x-axis, one's on the y-axis, you can get away without remembering what's x and what's y. But if we're given like 3 or 4 or 5 vectors that we have to add together, then it becomes really important to be able to distinguish between x and y. Because if you have 3 or 4 or 5 vectors to add together, like in themselves, you can't draw a right-angled triangle. You have to combine x's and combine y's in order to get that right-angled triangle. Before we do that, let's identify how much of each of these vectors is x. Remember, we're going to combine x's and going to combine y's if we have lots of vectors, but we have to figure out how much is x, how much is y. So let's take a look at example number 13, and we'll do this together. The first two should be not crazy hard. They get a little harder after that, though. Remember what we said a second ago? This is y, and let's do it the other way around. This is x, whatever's on this axis is x, and whatever's on this axis is y. So how much of the 10 meters is x? How much of the 10 meters is y? How much of that 10 meters is on this axis? 10. All of it is, right? All of it is. The x component of this is 10 meters. What's the y component of this? 0. None of it is on the y-axis. Okay, good. What's the x component of this one? 0, because all of it's on the y-axis. What's the y component of it? 7 meters. Good. So far, so good? So remember, don't forget the goal. We haven't really dealt with the goal yet other than that first little easy 3, 4, 5 example. But the goal is to get a right angle triangle. We're just building to that now with harder questions. What about the x component of this and the y component of this one? Well, let me first label the x component of this and the y component of this. We have a 10 meter vector at 30 degrees here. We're going to say that this is our x component of it. How much of that 10 meters is x component? Well, however long that side of that triangle is. I don't know what that is, but I know that whatever its value is my x component. And whatever's on the y-axis is my y component. So how do you think you're going to find your x and y components here? Not as simple as the first two examples, right? Any ideas? Sine, cos, tan. You guys remember this? So, katoa. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tan is opposite over adjacent. Hypotenuse is the easiest one to decide, the easiest side to determine. The hypotenuse here is 10. X is which? X is opposite or adjacent? Yes, it's adjacent. Good. Now, you say, well, how do you know it's adjacent? Adjacent is beside the angle. Then some of you are going to say, well, so is this one. The 10's beside the angle as well, right? X and the 10 are both touching the angle. But the 10 is already the hypotenuse, the longest side. So what's the other one that's not the longest one that's touching the angle? That's the adjacent. So if we're looking for x, we're looking for adjacent, we have hypotenuse. Which trig function are we going to use if we have hypotenuse and we're looking for adjacent? Which one goes with adjacent and hypotenuse, Marcos? Cosine. So let's do that. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. Now, we're going to do that on our calculators here. Follow along with me. First thing I'm going to do, this is completely aside, okay? First thing I'm going to do is every time you come into class and have to deal with angles, you should do this. Okay? Including quizzes, including tests, including every day in class when we're dealing with angles. The first thing you should do is this. Sine 90, which is, you look at this, sine 90, what does that have to do with this? It's a check. If sine 90 equals 1, you're good to go. If sine 90 equals 0.89, it means you're in radian mode, and you have to convert it back to degree mode. Now, how do you convert it back to degree mode? Let's go mode. You can scroll down here, you can see I'm in degree mode, but if it says radian, then highlight degree. Press enter, and then exit back. Does that make sense? Remember that when your calculator's cleared for a test in physics or in chemistry or math or some other subject, it automatically goes back to radian mode. That's why we always want to do that check. You can be in degree mode today, but next week you might be in radian mode because your calculator's been cleared for a test or because you ran out of batteries or something like that. So we're going to do that check. We're going to get in the habit of doing that check every time you need to do a calculation involving an angle. For the other calculations, it doesn't matter. but for angle calculations, it does. Okay, so there we go. Now let's find x. We want to get x by itself. We got to get rid of the 10. It's on the bottom. How do we take it to the top? Multiply. So we're going to say 10 times cosine 30 gives us an angle of x component of 8.6603. So how much of that 10 is x component? 8.66. Make sense? How much of it's y? Well, the y component of this is the one side that's not touching the angle. That's not hypotenuse, because hypotenuse touches the angle. That's not adjacent, because adjacent touches the angle. That's the opposite. Okay, if you're looking for opposite, and you're given the hypotenuse, which trig function is opposite in hypotenuse? Sine. So let's say sine 30 degrees is equal to opposite over hypotenuse. Y is going to be 10 sine 30. I don't need to do that check again. Once a day is fine. Now I'm going to say 10 sine 30. Does anybody know what sine 30 is, by the way, off the top of their heads? You're going to see when I do questions, when I make up questions, they often involve 30 degrees because sine 30 is 0.5 and it makes the math easier. So I often use 30 degrees. 10 sine 30 or 10 times 0.5 is 5. So first one, 10 meters, x component, 0 meters, y component. Second one, 0 and 7. Third one, 8.66 and 5. Does that make sense? Let's do a little poll here. Let's do the next one here. We've got 7 meters here at 50 degrees. How much is x and how much is y? Let's label this as x. Wait a second. How do we know to label this as x and not this as x? Well, in the end, it's the same value, but you want to label the first one that I labeled as x. Why not up here? I need to make sure the angle is touching that. Does that make sense? Like I need to make sure that when I draw my x and y components, I make a triangle, and the angle is inside that triangle. So I'm going to label that as x, and I'm going to label this as y. Now, remember our sine, cosine, tan, so katoa. Which side of the triangle is x? Which side is it not? Like which side is the easiest one to determine? Sorry? Opposite? Okay, you could say that, yeah, because opposite is the only one that's not touching the angle. Well, that's not opposite, is it? Because it's touching the angle, right? So it's not opposite. Okay, so we've narrowed it down to 2. It's not opposite. It's also not the hypotenuse. How do you know it's not the hypotenuse? Because that's the longest side. It's not the longest one. So it must be the adjacent. It's touching the angle, but it's not the longest one. So it's adjacent. We're looking for adjacent. We've got the hypotenuse. Which trig function? Adjacent and hypotenuse. Ah. So, koa. Cosine, right? Cosine 50 degrees is equal to adjacent over hypotenuse. So we're going to say on our calculator here, 7 cosine 50 gives us 4.94995. Now let's do the y component. Well, the y component, we're looking for the opposite side. That's the one that's not touching the angle. We've got the hypotenuse. Say sine 50 degrees is equal to opposite. This time it's 7 sine 50. 5.3623. Kind of making sense? Little? Okay, let's do the next one. This would be X, and this would be Y. Oh, you know what I just noticed? We could, if we want to, be a little more specific with the one we just did here. How? We're going, this 7 meters is going left and up, right? So the Y component is 5.36. We could say the X component is, like, negative 4.4995. Some people will choose to put in the negative here. Some people will choose to put it in later on when we actually go to use this number. That's up to you. We'll address that more later on, okay? Next one. X component is which side of this triangle? It's opposite. It's not touching the angle, right? So it's opposite. Which trig function goes with opposite and hypotenuse? Sine. So we use cosine for x component twice. Now we're going to use sine for x component. Sine 35 degrees is equal to opposite over hypotenuse. On our calculator, let's say 5.0 sine 35 gives us a value of 2.8679. Well, then your y component must be your adjacent then, right? It's not the hypotenuse, because it's not the longest side, but it's touching the angle, so it must be the adjacent. Cosine 35 degrees is equal to adjacent over hypotenuse. .0958. How much of this 5 meters is up or down? 4.09. How much of it's left or right? 2.86. We could be more specific here. If we decided to be, which one would we make negative? X, somebody said? X, you could say, is negative because we're going down and left. So we could make that negative. Is that it? Yeah, we could make the y component negative as well because we're going down and left. Not just left, but down and left. And finally, our last example here. This is x. This is y. How do I know to draw the arrows the way I'm drawing them? Like, how did I know not to draw that green arrow up? Look at the vector. 20 meters. Which way is it going? Right and down. Well, then draw the green arrow down, okay? Because it's going right and down. How did I know to draw the blue one to the right? Because it's going right and down. Ella? As a final answer, you can round, but I'd like you to leave the unrounded number in these, because generally when we're solving for components here, we're not at the end. Generally, like right now we are, like for what I'm showing you right now, but this is more of a tool that's going to be used as part of a bigger question. So normally when we're doing this, we'll use the unrounded number. I mean, realistically, you get around somewhere, right? Yeah. Like 4 or 5 decimal places is fine. Okay. Ideally, like you leave it to 100 decimal places, but you're not going to write that down. But you also don't want to write down just 1 decimal place. Most times, to be honest, it's not going to make a difference. But there's that, 1 time out of every 5 where you round, and you end up getting a slightly different answer because you rounded. So we want to be right 5 times out of 5, not 4 times out of 5. Right? Okay, x component here. Which side of the triangle is this one? Well, it's not the hypotenuse because it's not the longest side. The x component is Opposite, because it's not touching the angle, right? So opposite, we have hypotenuse, right? If we have opposite and hypotenuse, we're going to use sine. Sine 60 degrees is equal to opposite over hypotenuse. On our calculator, we say 20 sine 60. Do I need to do that check, sine 90? No, already done it. Like, unless somebody clears your calculator mid-class, you're going to be fine once you've checked it once. That gives us 17.3205. And then the y component, well, that's going to be the cosine function again. Cosine 60 degrees is equal to adjacent over hypotenuse. And 20 cos 60 should give me 10. 20 cos 60, 10. Is that okay? Here's what I'd like you to do now for the next little bit here, probably the remainder of class actually. Take a look at worksheet number 6, vector components. There's 8 questions on that page. The first 3 are like questions 1 and 2 right here. Then 4, 5, 6, 7, and 8 are all like the rest of the questions where you have to do sine, cos, and tan. Please do me a favor today, humor me. Even if your preference is the sine law, humor me today and use sine, cos, and tan for these today, okay? On a test, I'm not going to mark you wrong no matter how you do it, okay? But humor me today, at least get practice on sine, cos, and tan so you can make your own decision once you're comfortable with both on which one you end up doing. Okay, does that make sense?